We discuss now exercise number 4. First part of this exercise is we have some irradiance given. So before 6 a.m. there is no irradiance at all. And then it's 300 watt per square meter during the hours from 6 a.m. to 10 a.m. And then from 10 a.m. to 2 p.m. it's 600 watt per square meter, and then symmetrically in the afternoon it's 300 watt per square meter from 2 p.m. to 6 p.m. and after 6 p.m. the sun is set and there is 0 watt per square meter. That's simplified. Usually there's a continuous irradiance level, continuous moving irradiance level of the sun, but in order to simplify the calculation for you. According to the irradiance on the module temperature elevates. Before 6 a.m. it's quite cold, there is 20 degrees Celsius, then there's some irradiance and the temperature starts to rise. So we have here 30 degrees from 6 a.m. to 10 a.m. Then at 2 hours before midday, 10 a.m. until 2 hours after midday, 2 p.m., we have a temperature of 50 degrees Celsius. And while the ambient temperature is also rising, the temperatures in the afternoon are a bit higher than in the morning. So it's not symmetrical. So we have 40 degrees Celsius from 2 p.m. to 6 p.m. And after 6 p.m., probably at a tropical location, we have 20 degrees Celsius during the night. So the tasks are first, we make a drawing of the irradiance and of the irradiance curve and the temperature curve during that day. Then we shall calculate the generated electrical energy for a 10 kilowatt peak generator. This peak means under standard test conditions, including the irradiance and temperature influences. And last but not least, we will calculate the performance ratio of such a system. Basically, we calculate the temperature effects, not the spectral effects and the reflections. So let's start. So first we make this drawing. So we start making the drawing here, and just the green here is the irradiance value. So it starts before 6 a.m. There is no irradiance, and it starts to elevate to 300 watt per square meter. And 2 hours before and 2 hours after midday, we have 600 watt per square meter, and then it's going down symmetrically from 2 p.m. till the sunset to 300 watt per square meter, and after the sunset at 6 p.m. or 18 o'clock, this is 0 watt per square meter. Then we have the temperature values as told here. This is a right scale here. So we have 20 degrees before 6 a.m. and after 6 p.m. Then in the morning it starts to elevate until 30 degrees until 2 hours before midday. Then it starts to reach its highest temperature of 50 degrees. Then it's going down to 40 degrees and then in the nighttime again to 20 degrees. So how we calculate all this? So we can also make an analytical form, but what we shall do in this case, we shall make a division into several cases. So to divide the graph into several cases, because we have a nice constant values during some periods, we separate those periods. This is again the graph, and we separate first case 0 is before 6 a.m. That's quite easy because there's no irradiance, there's no output. Then from 6 a.m. to 10 a.m. we have case 1. Then from 10 a.m. to 2 p.m. we have case 2. And then we have case 3 from 2 p.m. till sunset. And then last but not least, we have 0 irradiance and 20 degrees of Celsius. That's our case 4. So we calculate each case separately and add up the generated electrical energy during these periods from case 0 to case 4. So first it's the formula. So the electrical energy being generated with W from time 0.1 until time 0.2. Usually use integral form, but while we have constant value during cases, we can do it in a more simplified form. We consider the adjustment in irradiance. While we have the actual irradiance is usually here, not usually, but it's considerably lower than the irradiance under standard test conditions. As you know, this irradiance under standard test conditions is 1000 watt per square meter, and here we have a maximum is only 600 watt per square meter. Then the second part here is considering the temperature influence. So we have here our temperature coefficient, TC, temperature coefficient. This index P symbolizes that it's for power. Then the temperature difference, and then we have the time period where we do consider that we multiply it with a number of hours. Usually we have constant values for 4 hours from case 1 to K3. The temperature coefficient is minus 0.4% per Kelvin, or if you do it without the percent, it's a minus 0.004 per Kelvin. We put in the numbers now here. Okay, as is just here mentioned, this delta T is the actual temperature minus the TC. As you all know, this operating temperature under standard test conditions is 25 degrees Celsius. But while we calculate here, temperature differences are given in K, so this is K. Some people use it also, temperature Celsius, the result will be the same. So first, K0, irradiance 0 watt per square meter, easy calculation. Output is also 0 watt hours, because if there's no irradiance, there is no electrical power output at photovoltaics. So then from case 2, we have an irradiance of 300 watt per square meter for durations of 4 hours. The temperature of the solar module elevates to 30 degrees Celsius. So we put in the numbers. So this is adjustment for the irradiance. So we have 300 watt per square meter divided by 1000 watt per square meter. Then we have here the temperature coefficient here, and the deviation from standard test conditions. Here we have 30 minus 25 degrees, and it takes 4 hours. And here in the beginning, we take the power under standard test conditions of our PV generator, which is 10 kilowatt. So we put here the number here, that is 10 kilowatt, 0.3 is the adjustment by the irradiance. Then here, this is the temperature effect, so we lose about 2% only due to the temperature. And this period is 4 hours. So during this 4 hours, we generate 11.76 kilowatt hour electrical energy. Let's go to the second case. So we have from 10 a.m. to 2 p.m., so 2 hours before and 2 hours after midday. The irradiance is considerably higher. It is double. So we have 600 watt per square meter. Temperature also goes up to 60 degrees Celsius. Sorry, was this 60 degrees or do we have 25 degrees? I calculate here for 60 degrees Celsius. We do adjustment later. I think it was 50 degrees Celsius here. Yes, it only goes up to 50 degrees. So the following calculation is done for 60 degrees. We give a correctment of this later. So we have here losses by a temperature of about 14% at 60 degrees Celsius. The irradiance values stays the same. So this is 600 watt per square meter divided by 1000 watt per square meter, 0.6. And then at the temperature of 60 degrees Celsius, we have a power output of 20.64 kilowatt hours. Yes, it's a repetition of the same formula, so you can see it also for the next cases. For the next case, K3, this goes from 2 p.m. to 6 p.m. Then we have a temperature of 40 degrees Celsius. So we have here the lower irradiance, therefore a factor of 0.3. And this is the impact of the temperature. We lose about 6%. So here's about 0.94 as a factor which considers the temperature, and duration is also 4 hours. So during this period, 11.28 kilowatt hours are being generated. After 6 p.m., 0 watt per square meter, temperature 20 degrees Celsius of the cell, but output due to the non-existing irradiance is 0 kilowatt hours. In total, if we add up this value, then we have here 0 plus 11.76 kilowatt hours plus 60.64 kilowatt hours for 60 degrees. I give you a correction later then, and 11.28 kilowatt hours. And together we have 43.68 kilowatt hours as a generation during that day. So we want to know the performance during the day, the performance ratio during that day. So we have here what is of interest for us. So we know this number already, the actual output of the actual generation of electricity. But we don't know what would be generated if we would have a constant cell temperature of 25 degrees according to the standard test conditions. The formula here is still the same, and we put in the numbers for 25 degrees. That's more easy calculations because we don't have any deviation from standard test conditions. So delta T here is always 0 for both cases. So we have 300 watt per square meter in the morning and in the afternoon, symmetrical here. So it's 2 times 4 hours, that's 8 hours. Then during midday, 2 hours before and 2 hours after midday, this is 4 hours. Also, for the 25 degrees constant temperature, we don't have any deviation. So if we add all up those, we have 10 kilowatt times 4.8 hours. It means we have a power generation, energy generation of 48 hours theoretically if we keep it at 25 degrees Celsius. Now we want to calculate that performance ratio here. So we just take this value and we take on the other part, take the already calculated 43.68 kilowatt hours divided by 48 kilowatt hours. So we have a performance ratio of 0.91, considering the 60 degrees which have been used there. So in reality, we will have a little bit later, a little bit higher performance ratio than this 91%. So the next part is, so now we want to know from which parameters depends the open circuit voltage of a solar cell. So the possible answer in this multiple choice are the spectrum of the radiance, the temperature of the solar cell, and the solar cell technology. So what's the reason for the open circuit voltage? That's the internal electrical field. So it's nothing to do with the spectrum and so on. This is just has an impact on the current, but not on the voltage. The temperature, we know already from the preceding calculation there is a temperature coefficient for sure, that's correct. And also, if you don't have silicon technology but other technology, you will have a different electrical field and therefore voltage will be different. So both of those are correct. Number 4b, from which parameters depends the short circuit current of a solar cell? Does it depend from the spectrum of the irradiance or from the level of irradiance? So sure, level of irradiance, that's totally correct, because this is the number of photons which comes in, which directly transform into a flux of electrons, and therefore is directly proportional. For the spectrum, we already know if you have a spectrum which is more matching with the spectral sensitivity of the solar cell, you have also a higher output. While the voltage stays constant, the output is defined by the higher irradiance. So both of them are correct. So next question is number 5. Why are the solar cells interconnected in series in a solar module? Is it either to increase the current, to increase the lifetime, to increase the voltage, to increase the PV conversion efficiency, or is it to reduce the temperature coefficient? Series connection means that the current stays the same. So first is totally wrong. Increase lifetime, why should be an impact on lifetime? Increase the voltage, yes, that's correct. We increase the voltage by that. And conversion efficiency, it's not really the case. Some new models, they have half cells, but in general, you don't increase, you increase the area efficiency of the solar module a little bit. But not really the PV conversion efficiency of a single solar cell. And to increase the temperature coefficient, that's also wrong, so no impact on that. Next question. If just the size of a silicon solar cell is increased from 10 centimeters by 10 centimeters to 16 by 16 centimeters, that was actually the case. The first generation of the solar cells only had 10 by 10 centimeters, and nowadays they are in the vicinity of 16 by 16 centimeters. First question is, how much is the increase in voltage? Second question, how much is the increase in current? Let's go for the last first. So the current, would it be increased? Yes, it would be increased because we collect a larger number of photons, and while the number of photons is proportional to the number of electron flux, and therefore the current, there's a direct proportionality to the area. Next is the increase in voltage. No, there is no increase in voltage because it just depends on the internal electrical field, and that is not dependent on the area. So here the current I is proportional to the number of absorbed photons, also proportional to receiving areas. So we have I increase according to the relation of the area. So we have 16 by 16 centimeters divided to 10 by 10 centimeters. That's a factor of 2.56, or in other words, 156% increase. And we already said the voltage increase is 0. Next question. I already marked them there. So from which parameters depends the open circuit voltage of a solar cell? So it depends on the strength of the internal field. So that depends on the solar cell materials and its technology and on operating temperature. For which conditions bypass diodes are important. So they are important when a cell is shadowed or a module is shadowed. The other factors are not relevant. How are the bypass diodes being connected? Bypass diodes are connected in parallel to the string and not connected in series. This is our string diodes, which are used for that if you connect them in series. And bypass diodes are portion or connected that are blocking conditions under unshadowed conditions. Otherwise, if they would be in conducting conditions, they would short circuit your solar cell. That's a thing you don't want. So under undershadowed conditions, they don't have to be activated, and they have to be in conducting conditions when there's a reverse voltage due to the shadowing of the solar cell. I'll give you further. I've made a nice animations on the bypass effect. I just showed one picture last time, but I give you an update on that so it's more understandable. Next part here, number 9, which components are responsible for the so-called weak light effect? The weak light effect occurs if you have lower performance at low irradiance levels, and that usually occurs while you have if you have a low irradiance level, what happens? The load resistor is then lowered because of a lower current. Voltage stays the same, and then this resistance in relation to the internal parallel resistance is relatively high. So we have a higher proportion of current being deviated here internally, and therefore the losses are relatively higher at low irradiance levels. At higher irradiance level, this resistor is relatively low, and most of the current goes through here, only a small part goes through here, and therefore this effect is almost neglectable. But for low irradiance levels, this gets important. So we have to consider this. Are there any other effects? Do we have an effect of the series condition? No, this is just the contacts. There is no effect. It just depends on the current, and when you have low current, there is even lower voltage losses there. Also, what we have, yes, the load doesn't have effect on the weak light effect, so it has to be adapted to stay in the maximum power point. But if it's well adapted, it doesn't have a negative effect on the weak light performance. Also, the diode, this should be an ideal diode. The non-ideality is represented by that resistor, and that is responsible for that. So we just have to mark that one. Next question is, what are string diodes? Are string diodes connected in parallel to a PV modules? Are string diodes connected in parallel to a string of PV modules? Or are string diodes connected in series to a string of PV modules? So what are string diodes for? They should avoid that current from parallel strings go into the original string. In order to avoid it, it's like a valve, so that they let just current go out but not go in. They have to be connected in series to a string of PV modules. Next three possible answers. The string diodes block the current into a string of modules if a string in parallel has a higher voltage than the string with the string diode. Is it true? Yes, that's true. You want to have this one. Next question. Next answer is the string diode conduct the current to a string of PV modules if a string in parallel has a higher voltage than the string with the string diode. No, you don't want this. You want to avoid that current that goes into your. So the upper was right. This is wrong. And last but not least, the string diodes always cause a voltage loss due to the breakthrough voltage of the diode. Is this true? They are connected in series. Yes, there is a voltage loss, and this has to be considered. Next questions are, what are the standard test conditions? You probably all know. So the air mass is AM 1.5. The irradiance value is, let's just also keep in mind, don't mix up the units, not watt times square meter, but 1000 watt per square meter is the right answer. Also, ambient temperature, is it relevant? Yes, it's relevant, but we have to fix temperature of the cell at 25 degrees. So the cell temperature is a reference conditions of 25 degrees. And what else is relevant? Yes, we have to have a perpendicular incidence on the solar module. Both terminal contacts are grounded. That's nonsense. If you have both terminal contacts are grounded, you don't have any output, power output at all. What is the fill factor of the PV module? So just you can describe it here via a formula or show it on a graph. So here it's the actual power output, so voltage times current in the maximum power point, divided by the ideal power output, open circuit voltage times short circuit voltage. Number 13, what does the performance ratio mean? It depends on which parameters. So the performance ratio depends on the operating temperature. Yes, we calculated already in the first part of the exercise. So here's a formula again here. You have here the actual power output divided by the power under standard test conditions, or the other ones we didn't discuss yet, but it's also true. We have the actual irradiance level divided by the power output under standard test conditions, and you find this number of full load hours or full sunshine hours can use also. But we stick for the first part, and as you already know, as we calculated, it depends on the operating temperature. The other three are next two are also true. Depends on the angle of incidence of the sun. It depends on the actual solar spectrum in relation to the spectral efficiency of the solar cell. I just pointed this out also. And yes, the standard test conditions are not relevant here because we want to have the actual power output. Next question is here, we have a solar module that operates in the maximum power point under 1000 watt per square meter, and there it needs ohmic load of 4 ohms to operate in the maximum power point. If we reduce now the irradiance level from 1000 to 250 watt per square meter, what does it mean? It means, sure, the irradiance is proportional, creates a proportional reduced current. So we reduce the current by 4 times, and you remember the ohmic law, voltage divided by current 4 times smaller. So we have an increase in the ohmic load by 4, so it's 4 times 4. So we have an ohmic load to operate the module in the maximum power point of 16 ohms. Next question is not so much related to the irradiance level, but to the temperature increase. So we have the same module. Here more details about that module: 32 volts in the maximum power point and 8 amps in the maximum power point. And due to the high irradiance, temperature is increased from 25 to 50 degrees. Temperature coefficients are given. So temperature coefficients for the voltage in the maximum power point is minus 0.5% per Kelvin. For temperature coefficient for the current is 0, and temperature coefficients for the power output is the same as for the voltage, minus 0.5% per Kelvin. So the question is what load we have to put there in order to still operate in the maximum power point. So we know already here it was 4 ohms. So if we have higher temperature, what do we expect? What's happening? So in general, we have a reduced voltage. So we have reduced ohmic load. That means it's not 4 ohms. So first estimation is somewhere below 4 ohms. And to calculate the exact value, we take a look at the formula here. So we have the voltage and the standard test conditions, and here the correction factor. So that's 1 plus the temperature coefficient voltage. That's that one here, minus 0.5%. And then the temperature difference, which is 25 degrees of temperature difference. So a minus 0.005 times 25 is minus 0.125, and together with 32 volts we arrive at 28 volts under 50 degrees Celsius operation. Then we calculate also the resistance. So we have here the voltage at maximum power point divided by the current at maximum power point. The current is no temperature coefficient, so it stays the same. So we have 8 amps. Here we have 28 volts. So we have here as a result 3.5 ohms. That's our result. That's what. Thank you very much.